I will present some slides that you guys know very much, just because I want to speak about it today. So as you know, the ultra-high performance concrete is has an ultra-high strength, high ductility, excellent durability. So a lot of people didn't call it concrete at the beginning. So then you know that it's a mixture of many powders. Cement, silica, fume, quartz powder, quartz sand, water superplasticizer, fibers, and no coarse aggregates. So I'm not just I'm repeating this by purpose because I want to discuss that later. So this is, everybody know this bridge at Sherbrooke, where I am from, and this is at that time that was the reactive powder concrete done by Bouygues and at the University of Sherbrooke with Pierre-Claude Aitzin at that time. This concrete was, just for information, 20 MPa, but when it's confined, it goes to, 200 MPa, sorry, then when it's confined, it goes to 300 MPa here in the tubes. Then after that, you know all the footbridge from Seoul in 2002, and also the Jean Bouin for architectural design, and also the Musen from Marseille and the Louis Vuitton in France. So this picture here from Vic's work, or reference to that Vic Perry at that time, just to show that, yes, you can have a very good sustainable structures or buildings or whatever just by cutting a lot of concrete. So the volume of concrete can decrease significantly with a very, very good mechanical performance. So you can you have less passive reinforcement, which is very good for sustainability. You have you can reduce the size of the pieces, etc. Also, you can see the durability of this concrete is amazing. All the performances on durability are really very good, going from the scaling to the ASR and everything. But so this is what I want to speak about today is we have a high volume of cement. We had a lot of people now try to decrease as they can the volume of cement. It requires high energy for mixing and consume a lot of products. But as you know, I don't have to tell you about the greenhouse problems, the global warming, etc. But this is the fact. So we have also high heat of hydration, shrinkage, and decrease on rheology. So also now something else that we don't speak a lot about is the problem of quartz sand for the health, because it's crystallized silica, and you know that for the lungs, etc., it's not very good at all, especially for the workers, and also high volume of silica fume, and you don't find silica fume everywhere. So our solution here is how to solve the problem. Of course, more and more work should be done on the packing density. So we went all through the packing density models. But what I am going to speak about today is the replacement of many of these materials, or at least we present two here, but we were able to replace three with recycled glass, or glass powder or glass sand. So why glass? Because it's have a very good mechanical properties, even as a particle, but also it's a pozzolanic. Now it's proven, and actually it's have ISTM standard and also and CSA standard also in Canada. The absorption is just amazing, is a 0. As said one of my students, thanks God for my bottle of wine. It's sustainable, healthy compared to the reactive quartz, and low cost. Well, was low cost. So just why glass at Sherbrooke is because from 2004 we worked a lot. I have an industrial chair, which is now almost 20 years working on different use of glass powder in concrete. We have many of people working with us, like glass producers, structure owners, concrete producers, admixture producers, even citizen groups. So, so if you want to see more about the work of the chair, you can go to the website. There are like 40 or 50 papers there that you can see. The glass powder is now like ground glass pozzolan in ASTM from 2020 and until 2018 in CSA too. So you can refer to that one when you speak about powder, not about the other particles. So what we did, so we played a lot with Nancy and other students, how we can replace all these materials here with different particles of glass. So we started with the glass powder replacing completely the quartz powder. The quartz sand, we replaced a part of the quartz sand, a part of cement, and also, I don't present that here, but we ground the glass very, very fine to around 2 or 3 micron, and we use it in replacement of a part of silica fume. So you can see here the particle size distribution of all those materials. This is what I told you, the fine glass powder, and the others are just like the same size like cement, and also you can have the glass sand here. So we worked on the filling all the gaps here. And I will show here some parametric study before to show some cases. So the cement was replacing glass powder, quartz powder, and the two together. So this is just a work that recently was redone by Begrish, Arilas Begrish, and when for the specialists in rheology, you can know that it's very difficult to measure the rheology of UHPC, but he used this was the ball system that what we can measure the rheology. So the findings are mainly that yes, the glass pozzolan increase the viscosity, but this material is just flowing, don't stop to flow. So the yield stress is very good. So it's just continuously viscous but continuously flowing. So when we work here with this is the slump. So you can see that as we add more glass and the slump is increasing from 0 to 50%, then the compressive strength also is increasing when the slump is low, but if you put very high slump, then you decrease a little bit your compressive strength when you replace a lot. So the optimums we found here is if you go to have high compressive strength, you can go to 20% glass powder. If you go to more flowable, then you can go up to 50% of glass powder. Now, if you replace the quartz powder by the glass powder, the same thing, you see the slump going up, and also you have the compressive strength, which is good at a given level. So you can, in this case, go to 100% complete replacement of the particles of the sand. Now, if you mix them, then you can classify your materials like 2. So if you want to go for more architectural application, then you have a very good flow and the material can fill up very well the molds. If you want to go to more structural, then you have to pay something about the slump, but you can get a high performance. So we compared here the compressive strength also with 2 days of the hot curing. So I didn't tell that, but in all the slides we did it on hot curing also to compare at 2 days. So then here you have classification of different type. So you go from semi-flowable to flowable to highly flowable, and also if you go to more definition of your surface in the architectural design, you can go to even more flowable. So we have different situations where you can use. Of course, you have to pay the price for flowability or for compressive strength, depending on your goal. And here, those are very basic calculation of saving on materials. This is just a simple calculation did by Nancy of her materials. You can see that you decrease a lot of the material, of course, to mitigate CO2. But then we did more detailed work where we compared many UHPCs, the standard one and the ones where we replaced it by fly ash or slag, whatever. So those are the classical UHPC. You can see here the high volume, the high quantity of CO2, and you can have a large bunch of compressive strengths. But when you go for replacement with the other materials, you can see here, of course, you decrease the CO2, but you have to optimize better if you want to have a higher compressive strength. And those are our UHPC with glass powder, where the rheology, the fluidity was good, the compressive strength was good, and the CO2 emission was decreasing, of course, because we are replacing a lot of particles there. So, as I told you, this is not me who is telling that about the quartz, so be careful. This is from the health group in Canada who gave that note. And now I speak about the field applications. So the first application, University of Sherbrooke allowed us to do a bridge here. The only way to do the bridge is because the president office is here, and we had to show him first the picture of the bridge, and then he said yes. So in place of doing one, we did two. So, but this is, you know, we have a lot of replacement of material like glass powder, and the compressive strength was a little below at 28 days, but increased significantly. And however, we don't really need the high compressive strength in that case, but it was very good. And this is all what I show here are already published in the different papers. So Joris Deschamps did the life cycle analysis of that bridge, compared to the one that the university wanted to do before, and compared also to the UHPC classical one. And you can see the values here of different parameters. You can see that climate change, ecosystem quality, human health, resources, etc. Very, very good demo, and it's also published if you want to look the paper. And this is actually was in the Concrete International journal. This material now is patented in U.S., Canada, Brazil, and Europe, and owned by BPDL in Canada. So let's speak about now the buildings. So this is what actually BPDL is doing with that material. So you can see here, this is a multi-store parking near the University Laval here in Quebec. You have this kind of panels. You can see here how the details, and also I forgot to speak about the color also. The color is very light. It's not very dark like with a lot of cement or silica fume. So you can have a very nice colors. A very good example of case study is I would love to have done this presentation in last convention in Boston, because you can walk down to Boylston Street. I'm sure if you are from Boston, you have to know the Boylston Street. And this is the Emerson College. It's a very old building, 1917, and this is the first building in US, which was when they did it, they do also these forms that we just can do normally with rocks or with a panel, really with so you have to have this kind of design here. So why the architect selected the UHPC? So because they wanted to renovate completely the building. They want to put it down and rebuild it. But that after they wanted to retrofit just the facade. So the UHPC for them it was, has ability to take on any form, such as replicating exactly what I said here, the carving, fit within the existing wall thickness here, and addition of insulation. So what they did, they used a laser technology, a very fancy one. They completely draw again the building so on 3D. Then they gave these 3D results to the company, which is a BPDL, to produce the molds. So the molds, when they are produced, then they are fitted with UHPC. So what they did really is they replaced this section here. So it's 1,500 panels, and they just fixed them on the surface. So they removed this and they fixed the panels there. So you can see the type of the panels produced. It's a precast. And just information, this is normally steel, but this is UHPC. So they replace completely just by the color. So this is the actual building, how it looked like. And really it's very, very nice. I was there at last convention. And here you can see the style of the material and also the definition of the carving there. And this was done in 2019, so it's a very, very nice job. So the ultra-high performance concrete can be designed using ground glass pozzolan and glass sand of different particle size distributions, depending on which material you want to target and what's the compressive strength or the slump you want to target. You can play with architecture application and structural application. And for structural application, there is actually ongoing discussion to have something in Canada. So then, thank you very much for your attention.